Hello and welcome to G Fun Facts Online, the show that dives deep into the biggest questions of our universe. Today, we're talking about monsters. Not the kind under your bed, but the kind that swallow light, warp space-time, and lurk in the darkest corners of the cosmos. We're talking about black holes. For centuries, they were just ghosts in the math, theoretical phantoms born from Einstein's equations. But what if I told you that today, we are no longer just looking for them, we are building them, not in a lab, but inside the most powerful supercomputers on Earth. We have become digital architects of the cosmos, simulating the very birth of black holes to unlock their deepest secrets. So how do you build a universe in a box and watch a black hole come to life? Let's find out. To simulate the universe, scientists have to translate all the rules of reality into code. Everything from Einstein's general relativity, which governs gravity and the curve of space-time, to the chaotic physics of superheated gas and magnetic fields, gets turned into algorithms. This cosmic recipe is then fed into supercomputers, colossal machines that can perform quintillions of calculations every single second. These simulations, like the Millennium TNG project, can track billions of digital particles across billions of light years, watching how the universe evolves. But now, they can do something even more incredible. They can zoom in, with stunning precision, on the life and death of a single star to witness the exact moment a black hole is born. One of the most common ways this happens is through a collapser. Imagine a star many times more massive than our Sun. After burning for millions of years, it runs out of fuel. The delicate balance between its outward radiation pressure and the inward crush of its own gravity is broken. The core implodes catastrophically. For a brief moment, it becomes a proto-neutron star before collapsing completely, vanishing from sight and leaving behind a black hole. For a long time, astronomers thought these events would be quiet, almost invisible disappearances, calling them UNOVAs. But recent simulations are changing the story. They suggest that just before the star's final collapse, it might let out one last, brilliant flash of light, a final scream before it's gone forever. Astronomers are now actively hunting for this specific signal, a potential birth announcement for a brand new black hole. As dramatic as a collapser is, there's an even more violent way to forge a black hole, a cosmic demolition derby between two neutron stars. These are the super-dense corpses of smaller dead stars, so dense that a teaspoon of neutron star material would weigh billions of tons. Using one of the world's most powerful machines, Japan's Fugaku supercomputer, researchers recently modeled what happens when two of these objects collide. The simulation took a staggering 130 million CPU hours to run, but it captured the entire 1.5-second event in breathtaking detail. It showed the two neutron stars spiraling towards each other, warping space and sending out ripples of gravitational waves. It showed the moment they merged, the emission of ghostly particles called neutrinos, the eruption of powerful magnetic fields, and finally, the birth of a black hole and the launch of a powerful jet of matter traveling at nearly the speed of light. These simulations are absolutely essential. When our detectors on Earth pick up gravitational waves from such a merger, we can now compare that signal to the simulation to understand exactly what we're seeing. But the black holes born from dying stars and neutron star collisions are just the little guys. The real titans of the cosmos are the supermassive black holes. These are the behemoths that lurk at the center of nearly every galaxy, including our own Milky Way. And they can be millions or even billions of times more massive than our Sun. The big question has always been, how did they get so big, so quickly, in the early universe? It's a cosmic puzzle, and once again, supercomputers are providing the clues. One leading theory, explored by the Renaissance simulations on the Stampede 2 supercomputer, points to rare, super-dense pockets of gas in the primordial universe. In these special regions, the gas collapsed so rapidly and violently that it skipped the normal process of star formation and instead created a massive black hole directly. This gave these black holes a head start, allowing them to grow to enormous sizes in a relatively short amount of cosmic time. Another powerful theory involves galactic cannibalism. The Astrid simulation, run on the Frontera supercomputer, provided strong evidence for this. It showed that during a period known as cosmic noon, about 10 billion years ago, the merger of three massive galaxies could create an ultramassive black hole. As the galaxies collided and merged, the supermassive black holes at their centers would eventually spiral in and coalesce, forming a single, even more gigantic entity. Incredibly, the galaxies created in the Astrid simulation look almost identical to the ones we actually observe in the distant universe, giving this theory a huge boost. One of the biggest hurdles in this field has been bridging the vast difference in scales. How do you simulate a gas cloud that's part of the enormous cosmic web, millions of light years across, and also follow its journey all the way down into the swirling disk of material, just a few light hours wide, that's feeding a single black hole? Recently, a team at Caltech achieved this with a groundbreaking super zoom-in simulation. The project, a combination of two collaborations called FIRE and STARFORGE, completely upended a long-held belief about black hole accretion disks. For decades, theories suggested these disks, which are the source of food for a black hole, should be thin and flat, like crepes, but the new simulations showed something different. They revealed that magnetic fields play a far bigger role than anyone thought, puffing up the disk and making it thick and fluffy, more like an angel food cake. This fluffy structure isn't just a theory. It also helps explain the images we've actually seen of the black holes at the center of our Milky Way and the galaxy M87, taken by the Event Horizon Telescope. The future of this field is getting even more exciting thanks to artificial intelligence. These simulations produce petabytes of data, far too much for humans to analyze alone. AI and machine learning are now essential tools. For example, by training a neural network on millions of simulated images, astronomers were able to analyze the real data from the Event Horizon Telescope and discover a mind-blowing fact. The black hole at the center of our Milky Way, Sagittarius A star, is spinning at nearly its maximum possible speed. In a final fascinating twist, scientists are now bringing black hole physics out of the computer and into the real world. By creating a quantum tornado in a vat of superfluid helium, which has zero friction, researchers can mimic the gravitational environment right at the edge of a rotating black hole. This allows them to explore the bizarre quantum effects that are thought to happen there, providing a tangible way to test the fundamental laws of physics. From the silent death of a star to the chaotic dance of merging galaxies, the story of black holes is one of cosmic creation on an unimaginable scale. Thanks to the power of supercomputers, we can finally witness these events, test our wildest theories, and uncover new cosmic surprises. Each simulation is a journey back in time and a leap forward in our quest to understand the universe. Thanks for listening to G Fun Facts Online. Join us next time as we explore another of the universe's incredible secrets.